class. All right, so we're going to look at the potential around an electric dipole. So just a reminder, a dipole, we have a positive charge and an equal negative charge separated by a distance d. So they're equal charges. And generally these charges are very close together compared to, we want the potential at some point P outside. And so, the distances from these charges to the point is much greater than the distances between the two charges. And so we treat this dipole as like a single object. So that's why we placed this point above the center of our coordinate system, or the origin of our coordinate system. The other charge, they're equally spaced. So basically this is a dipole at the origin of this coordinate system, and we want to know the potential at this point at a distance r. And so we kind of, let's call the distance from the positive charge to PR1 and from the negative charge to PR2. Okay, now we can write down the potential very easily. Potential at point P. We've got our constant, and then we'd have Q over R1, and then we'd have I'll write it all out. Okay, so just the KQ over R for each charge. Now we can factor out this 1 over 4 pi epsilon naught and the Q. So we have 1 over 4 pi epsilon naught, or we're going to say Q over 4 pi epsilon naught times 1 over R1 minus 1 over R2. Or combining it into a single fraction, that is the potential at this point P. And this is exact, but it's much more useful if we make this approximation. So let's mark off this distance here. So we're breaking this up. Let's say this distance here is R1. So we mark off this distance from P equal to R1. And then this distance would be R2 minus R1. And again, these points are very close together. So we're going to treat this as like a dipole at the center. And we're going to find our dipole as a vector. I actually want to zoom in. I'll do this off to the side. We define this vector P as our electric dipole. And it points from the negative charge to the positive charge, and the magnitude of P is just Q times D. So the charge times the distance separating them. And so we're treating this as like a single object at the center. And so we have this R going to point P. Now let's say theta is the distance between the dipole vector, and like this, we can define this radius vector as well. So theta is a difference between these two vectors. So we have to define the dipole vector so that P points from negative to positive, and theta is that angle between them. Now, in this approximation, that say R is much, much greater than D, let's write that here. R is much, much greater than D. We can say R1 and R2 are approximately equal to R. Like the actual distance, the difference between R and R1 or R2 is too small for us to worry about. And so that's one approximation we can make. And let's look at this picture here. We have this angle here is theta. Basically, these lines are essentially parallel. So we say that that is theta. And from this triangle here, we can say cosine of theta is d over R2 minus R1. So R2 minus R1 is d cosine theta. So here we have the potential at point P. Is we have to take this 1 over 4 pi epsilon naught by itself. And then we have Q times d cosine theta. And R1 and R2 are each approximately equal to R. So that's R squared. And remember, Q times d is just the dipole moment. So we can write our final result. And we can write it as P cosine theta divided by R squared. So this is the potential at some point near a dipole. So again, this approximation is far more useful than this exact value here. So we consider a dipole like a single object at the origin of this coordinate system. And this angle is the angle, from the dipole to the point. It's the angle between the dipole vector and the radius vector that points to point P. And so this is the potential due to a dipole. And notice that the potential drops off according to the inverse square law, where for a point particle, the potential is inversely proportional to the distance. For a dipole, it's inversely proportional to the distance squared. And so the potential drops off much quicker. The electric field due to a dipole is much weaker than a point particle because essentially this dipole is an uncharged object. The only reason an electric field exists around it, like at this point P, for example, if we draw it, we have P, we have an electric field due to the positive charge, and then we have an electric field due to the negative charge, and they almost completely cancel out. The electric field due to the negative charge is a little bit weaker in this case because it's farther away from the negative charge, and they don't perfectly line up because of that separation. But again, these two vectors mostly cancel out. So the electric field and the electric potential around a dipole is much smaller. So it drops off by this inverse square law. And we saw earlier the electric field goes as this inverse cubed law. So that's it for electric dipoles, and leave it at that.